Hello. Okay, in this video, I want to talk a little bit about representing a data set and specifically using box plots to do that. A box plot is a way of showing how and where a data set is most distributed by representing various markers within that data set. So here I've got a couple of data sets similar to what you'd be working with in say part one of the lab. This data is meant roughly to kind of look like that data would look. So you can see how the data set is set up. I have a column for trial number. So this would be if I were rolling my ball along my flat plane for a certain amount of time, and I did that 9 times. That's what the 9 trials here represent. And then below, if I took 9 more trials, but I doubled the time. So my second column is time, and I'm setting my time to be something, measuring displacement associated with that, and then doubling the time and measuring the displacement associated with that doubled time. So I kind of have 2 different data sets here. And a question I could ask is, how spread out are these data sets? Where does the data mostly lie? Are there a lot of outliers? And then finally, how do the 2 data sets compare to each other? And those are questions that you'll be answering in your lab report. And I want to talk about box plots as a way to do that. So first, before I show you what a box plot is, I just want to let's look at the data here for a sec and get a sense for how much spread there is and how you can start thinking about that. There are many ways you could maybe do that. A common way is to look at an average value. We're going to use a median value instead as sort of the middle point of our distribution. If I were to sort this data, so let me highlight the data here. If I go to data, sort range, I'm going to sort it by high to low in displacement. So column C is my displacement values. So I'm going to sort it from A to Z. That goes from low to high, I guess. So I've sorted from the smallest value in the data set to the highest value. I had to include everything here so I can preserve the trial information if I ever want to unsort it. But you can see my lowest value in this data set is 43. So the smallest displacement I got when I rolled it for 1 unit of time was 43. The highest was 52. So my data goes from 43 to 52. We'd call this value here the maximum value. The maximum value, this value, the minimum. The median value is the one in the middle. So right here, this is the median. So just sorting it and picking out the middle value, that gets you the median. And there's 2 other markers here that we're going to use. That is the median of the smallest 5 values, or the smallest half of the data set, and the median of the largest 5 values. For the smallest 5 values, that's called the first quartile value. The median of the top half of the distribution, that's called the third quartile. Really just ranking the values and picking out these sort of median values. So you can see we're splitting the data set based on how many data points we have in different areas. And what we're going to do is we're going to represent this graphically. And if we represent it graphically, we'll get a sense of where the spread in the data is. And the way to do that is with a box plot. What we'll do with a box plot is we'll take these values and we'll put them on a graph. So let me show you that. So if I go over to Desmos here, I've actually put the 2 data sets in here already. I've called the first data set that we were just working with A. And A is equal to this set of data. And the way Desmos knows it's a set is I've got these brackets here on either side of the list. This list doesn't have to be sorted. In fact, I copy and pasted it before I did any of the sorting. And what I'm going to do with this is I'm going to do something called box plot. There's a function in Desmos called box plot A. So I'm box plotting that set of data. I'm actually going to move it so that it's right on the axis there. Okay, so let's look at this. Here's what's happening here. The middle line that I've got right there, that's the median value. The closed off box here, that closed off box, that's the range from the first quartile value to the third quartile value. So that is the middle 50% of the data is in that closed off box. And you can see it's not really symmetrical about the median. That's because the data can be located in different places. The median isn't intended to be symmetrically the average point of the data set. It's just what's the middle value of the data set. And these little markers that go out further that kind of look like error bars, that's the minimum and the maximum value. So there's 5 markers here. There's a minimum, a first quartile, a median, a third quartile, and a maximum. And there's a few things you can conclude from looking at this. First is that, there's a spread in the data. And also that spread isn't equally distributed above and below the median. The data is more scrunched up at the low end. So that is, we're getting more values between the minimum and the median that are closer together. And the data is more spread out above the median. So we're getting a larger spread of the upper 5 data points between the median and the maximum value. What that means, who knows? That'll probably be more specific to your case, but you can start thinking about reasons why you might get data scrunched up in some places and more spread out in certain places based on the way you did your experiment and the sort of errors you were seeing present and the randomness that might be introduced into your experiment by various errors. Okay, so that's what a box plot looks like. It's a way of representing where data points are in a distribution graphically. Let's look at the second data set. So my second data set, if I wanted to compare it to my first data set, I could do a similar sort of thing here. I could sort it and do the same thing. So I'm going to sort by column C and go low to high again. So my lowest value, that's my minimum. My median is the one right in the middle, my 5th one in this case, because I have 9 data points. My maximum value is up here, and then I've got the first and third quartile values. First quartile and third quartile. So in this case, because I have nine data points, it's just the first value is the lowest value is the minimum, the third lowest is the first quartile, that is the median of points 1 through 5. The 5th value is the median, the 7th highest value is the third quartile, and the highest value is the maximum. If you have a larger number of data points, you just kind of scale outwards. So the median will always be just the middle value that you have if you sort everything from top to bottom. The minimum will always be the least value, the maximum will always be the highest value, and the first quartile value will be the median of the lower half of the data set from the median on down. The third quartile will be the median of the data set from the median on up. It'll always work out that way. 9 is just kind of a convenient number here. You can see the spread goes from 75 at the minimum to 92. The spread's a little bit greater than in our first box plot, just looking at it that way. And you might think about that as a point of comparison. Like, is there something, I just made up this data, but if this was your data, is there something that's a slightly more, that introduces slightly more randomness or slightly more error to this test with a time of 2 than for a time of 1? That's one of the things you could look at just here briefly. Let's do a box plot of that data set too. So if I go back to Desmos, I have B in here already. Again, it's not sorted, doesn't have to be sorted. Box plot B, I'll move that down to the axis 2 with the offset. I'm gonna unclick exclude outliers. It doesn't really make a difference in this case, but we're gonna keep all the data that we have. And you can see that comment I made earlier about the spread in the data being larger for the time equals 2 data set, what is data set B here. There's a larger range here than for our previous data set. That's interesting. Obviously, these ranges are much different. There's no overlap in the data sets. And we would say, because these data sets are so far apart compared to how wide the box plots are, that these are significantly different data sets, which, if we think to the physics, of what's happening in the situation, we would definitely expect them to be significantly different, because we have a ball that's rolling for double the time on a flat surface. We wouldn't expect those two things to be similar or the same. We would hope to have small enough error that we can distinguish the displacements we're getting when we double the time in this situation. So that is working. And now once you have this, the goal would be to interpret it. So you can look at how far apart they are. Where are the medians relative to each other? How much spread is there in one data set relative to another? And all of those things will be, you have to compare to your expectations for what you would expect to see for these data sets. But the box plots are a really nice way to represent the data sets graphically, where you still get a lot of information about what's happening in each data set, but broken down in a way that's easy to visualize. Okay, one last thing I want to do before I end this video. I just want to do a little bit of labeling. So I've moved this over, this image over from the box plots that were printed onto my iPad so I can draw on it. So let me label some stuff here. So to be really explicit about what's happening, on this box plot graph, the x-axis means something. So the x-axis here is displacement. And the units of that were centimeters that I was using. So that's the meaning of the x-axis. The y-axis really has no meaning here. Those numbers don't mean anything in this context because we're just comparing the displacements. So really it's just sort of you might be able to get just a one-dimensional line, number line in Desmos, but I'm not skilled enough with Desmos to know how to do that. But really, we're just looking at kind of a one-dimensional comparison between the displacements in these two data sets. So it's not a graph in the same way where we're looking at a relationship between time and displacement exactly, although we're just representing the data sets and the different displacements from the two data sets here. So to label things explicitly, this value in the middle, that's the median value for the data set. I guess I should label this too. This one is the time equals to 1 unit data set. And this is the time equals to 2 units data set. So the median is that one in the middle. In both cases, there's the median. You could compare the medians directly, but obviously there's a lot more information contained in the box plots. Looks like the median for the low one's about 45. And the median for the high one's about 85 or so. So not quite double. And if you were interpreting this, you could think about whether you would expect the medians to be, or these two values to be, to have the relationship of as you double the time, you double the displacement or not. There's the third quartile here. There's the maximum here. There's the first quartile here, just to be really explicit with the labeling. And then this little one, that's the minimum. It's totally possible to have two of these values fall on the same thing. So for example, if I had I could have a minimum value that was like 42 and a first quartile value that was also 42 if I had repeated measurements of 42. If I had enough of them, that might make up, an entire quarter of the data set. That's totally possible. And then you just see kind of one line here representing both the minimum and the first quartile. And in some ways that tells you that the data is really scrunchy right there. So I would be getting like very similar measurements at the low end. And to be really explicit on the other side too, there's the minimum value. There's the first quartile, and so on. I'll label these the same as the other side. What I'll do is I'll put that Excel worksheet up, and I'll put this image up too when I upload the video, so you can have it as a reference for how to build these things. I would really suggest you use Desmos to build your box plots because it's so simple, although you got to make sure that you understand the box plots that are coming out. And we'll spend some time in class interpreting the box plots. I didn't spend a whole lot of time here talking about how to interpret them, just how to construct them and what broadly they're showing. So we'll spend more time actually interpreting them using the physics that we know and using your knowledge of your setups. But that's a really brief introduction to box plots, and I'll see you soon. Okay, bye.